A second type of chemical bond is called a covalent bond, and covalent bonds occur when atoms are sharing electrons. So let's see how that works using a very simple example of hydrogen atoms. If we look at hydrogen's entry on the periodic table, we see that it has an atomic number of 1, which means that it has 1 proton in its nucleus, and we'll give it 1 electron in that first shell. If we have a second atom of hydrogen nearby, it would be the same, 1 proton with 1 electron orbiting in the first electron shell. Now, hydrogen does not have a full outer shell, so it is unstable and it will participate in chemical bonds. Rather than transferring 1 electron from one atom to another atom, these atoms are going to share electrons. So this atom will share its electron with the other hydrogen, and the other hydrogen will share its electron in return. Keep in mind that electrons are always moving. So this electron now is not just orbiting around one atom, it's going back and forth, being shared between both. The same is true of this electron. It is now no longer just orbiting one hydrogen, it's going back and forth between the two. That is a covalent bond. We have 2 shared electrons that are going to bind these 2 hydrogen atoms together. So a simpler way of drawing that would be to draw 1 hydrogen and then a straight line connecting to another hydrogen. The formula, the molecular formula, would be simply H2, that's hydrogen gas. Let's look at a more complicated example, slightly more complicated, starting with oxygen. Oxygen has an atomic number of 8, so we will start with a nucleus that has 8 positively charged protons. Then we'll add our electrons. We're going to have 8 of them, so we'll put 2 in the first shell, and that leaves us with 6 for the second shell. 1, 2, 3, 4, 5, and 6. We know the second shell can hold 8. It only has 6 right now, so the outer shell has vacancies, which means that oxygen is unstable and will participate in chemical bonds in order to fill those vacancies. Now, if we have, let's say, a hydrogen over here, 1 positively charged proton with 1 electron orbiting in the first shell. These 2 can share electrons. So the hydrogen will share 1, the oxygen will share 1 back. That's oxygen, this is hydrogen. And now those electrons are going to be moving back and forth from oxygen to hydrogen. So we have 2 shared electrons here, meaning we have a covalent bond formed between this oxygen and hydrogen. Now, when we do a little bit of accounting for electrons, we can see that hydrogen has that first electron that it started with, but now it's also sharing this one with oxygen. So when we're counting to find out whether or not hydrogen has a full outer shell, we count both of these 2, and we would say that yes, hydrogen is full, so now it is stable, and it doesn't need to form any other chemical bonds. On the other hand, if we look at oxygen, oxygen has the 2, 4, 5, 6 that it started with in its outer shell, plus the addition of this one that it's sharing with hydrogen. So now oxygen has access to 7 electrons, but we know that it needs 8 in order to be stable. So let's add another hydrogen on the opposite side, its proton and its electron. These 2 can be shared back and forth, and that will make oxygen stable because now it has access to 8 electrons in its outermost shell, and this hydrogen is stable as well because it is accessing those 2 electrons for its outer shell. This one, this molecule, an oxygen bonded to 2 hydrogens, we would write that as H2O. This is the all-important water molecule. Now we have two molecules. Both are formed by covalent bonds, but the type of covalent bond differs. Over here, we have what's called a nonpolar covalent bond because the electrons are shared equally. Over here, we have what are called polar covalent bonds because the electrons are shared unequally. Okay, so let's go here for a second. Every element has an electronegativity value. Electronegativity, you can think of it as a measure for how well does that atom pull electrons toward itself. If we have one hydrogen bonded to another hydrogen, they have the exact same electronegativity, so they are going to share these two electrons equally, which is why this bond is nonpolar. So in other words, we can think of these electrons going back and forth and spending an equal amount of time with both hydrogens. That is not the case over here with water. In the case of water, oxygen is more electronegative. So if we were to think of a covalent bond as a tug of war for the electrons, oxygen is always stronger. That means it's going to spend more time with those shared electrons. So we can imagine these electrons are moving around the oxygen, and then they will go back and spend a bit of time with the hydrogen, but then they're going to come back and spend even more time with the oxygen. So it's an unbalanced sharing. Now the consequence of that, because electrons are negatively charged, that's going to give the oxygen part of this molecule a slight or a partial negative charge. And we can represent that. Let's see, I'm going to draw it over here. So there's my oxygen, one hydrogen, and a second hydrogen. Because oxygen is so good at pulling electrons toward itself, we say that it is highly electronegative. It has a partial negative charge. And for the hydrogens, remember that when they're balanced, it's one positively charged proton with one negatively charged electron, and those two are a perfect balance. They cancel each other out, making hydrogen neutral. But when hydrogen is participating in this bond, that electron that it had is spending more of its time with the oxygen, and that gives hydrogen a partial positive charge. So we can represent that like this. So a polar molecule has two opposite ends. It has a negative end and it has a positive end or a positive side. Now, one last type of interaction is a hydrogen bond. I'm going to draw one more water molecule here. Here's our partial negative and our partial positive. Remember when we talked about ionic bonds, we said that in chemistry, opposite charges attract. So here we have a partial positive in close proximity to a partial negative. So there will be a weak attraction formed between those two. And that weak attraction is called a hydrogen bond. Hydrogen bonds are different than covalent bonds in some very significant ways. And that first way is that hydrogen bonds are comparatively very weak. So this is a very weak interaction in comparison to these covalent bonds, which are much, much stronger. Another difference is that hydrogen bonds are intermolecular. The prefix inter means between, and molecular just refers to the molecules. So here we have one hydrogen molecule and a second hydrogen molecule with the hydrogen bond going between those two molecules. Covalent bonds, on the other hand, are intramolecular. because they are within the molecule. They hold the water molecule together, whereas hydrogen bonds hold two different water molecules together.